All right, guys. So there are a few videos already posted about refraction of light, lenses, mirrors in the canvas shell. So what I'm going to do here is just to show you a few solutions for the optics section of the course. So I think I'm going to go also into lenses and mirrors here because might as well cover the whole aspect. I mean, optics is not that difficult. It's reflection of light, refraction of light, mirrors and lenses, which are applications of reflection and refraction. All right. But there are a few problems that might be a bit challenging or confusing. Like, for example, I was taking a look here at the scuba diving problem. That's a refraction problem. It's a classic refraction problem. That's from CENGAGE, by the way, problem number 6. So you have a scuba diver that is sees the sun at an apparent angle of 28 from the vertical. Look, guys, they tell you everything you need to know there. This is water. You always need a normal. I go over this in the lecture. And then you have a scuba diving here, looking at the sun at an apparent angle. So this is the scuba diver here, diver. And he or she looking at the sun, an angle of with 20, an angle of 28 degrees with a vertical. That's the vertical. What's the actual direction of the sun? So if you think about it, guys, you're going from water to air. Air has an index of refraction of 1, while water has an index of refraction of 1.33. If you're going from a region of a higher index to a lower index, the ray of light is going to bend away from the normal. The opposite as if it was going from air to water. So the way you want to draw the refracted ray is like this. See that? And that's the angle theta 2, theta 1. But the actual direction, guys, the sun is going to be, if I extend this around here, that's the sun. The direction of the sun is always with respect to the horizontal, though. So if I apply a Snell's law here, I get N1 sine of theta 1 equals to N2 sine of theta 2. Now, that's theta 1 for N1 and N2. Yeah, I know. Normally, air is the first medium, but not in this case. You're going from water to air. So 1.33 times sine of 28 equals to 1 sine of theta 2. So sine of theta 2 is this. Yeah. So you have to grab your calculator. I get 0.62. So if you do the sine inverse of that in the calculator, you just type sine to a negative 1. So here I may look. Okay. So arc sine, I get 38.32 degrees. Nice. So that's the angle. But is that the direction of the sun? Nope. The direction of the sun is 90 minus that. which will be 51.78 degrees. That's the direction of the sun. All right. There you are. This one. Apparent depth. I'm going to show you the problem in CENGAGE. That's what happens when when there is refraction, by the way. Objects appear at apparent depth, at apparent positions due to the refraction of light. So they give you a graph there of the actual position of a fish and the apparent depth. So you look at the apparent depth and the actual depth, right? So according to the person outside, the fish is at 1.13 meters below the ocean. What's the actual depth? So we need to, well, we're gonna redraw that here. And the way you guys are gonna do this is you have the water, I'm gonna draw it like this. And you have the normal. They give you all that in the problem. And you have the fish. And you have the important to look at the direction, right? See that? This is water here. So if you were to extend the refracted, here is where you will see the apparent position of the fish. This is 1.13 meters. So the confusing part is that you're not giving any angles, but you have to think in terms of your geometry. Oh, they give you the horizontal distance of this. They give you the horizontal distance is of 1.49. In this right triangle, you can observe that you do have this angle. This angle is this angle here. Right? Yeah. So if you got this angle, you can find the angle of refraction. Since you're going from air to water, you can find this angle here, then you can find the actual depth. So how do I find this angle? I have the opposite and I have the adjacent. Let's call this angle theta. Theta. This will be theta 2. theta 2 is 90 minus theta. Well, I mean, technically you can just find that, right? But let's do it like this. So theta, opposite of adjacent, tangent of theta is 1.13 over 1.49. Let's see what I get for theta and then theta 2. You see, this is a trigonometry type of problem. Yeah. If you are wondering where you're going to use this in school, well, 0.76. There you have it, right? So I get 37 degrees. I'll just round it to 37. So this is 37 degrees. So this angle is 53 degrees. So I found this to be 53 degrees. And that's basically it, because now with refraction, I can find theta 1. If I find theta 1, well, guess what? I can find the real depth. I can find the real D. Because this distance is the same, 1.49 meters. Theta 1, all right. Water to air. So it's like that one I just showed you. Water to air. Always the angles respect to the vertical. So sine theta 1 is sine 53 over 1.33. So I need to remember how to change. Okay. Yeah, 0.6. So that's gonna be 37 as well. All right. 0.6. So theta 1 is about 37 degrees. All right. Coincidence, that's the numbers I made. So if that's 37, I can find yeah. So now this over this. Opposite over adjacent. So tangent of 37 is opposite over the distance. So how do you solve? I'm not going to assume that you guys can do this, by the way. Sometimes algebra, right? That equals, so D goes here, this goes down. So D is 1.49 divided by the tangent of 37. Which is 3/4, by the way. Yeah, I get about 2 meters. $1.97. 1 to 2 meters. So that's another interesting problem of refraction. All right. There are a couple of problems in CENGAGE. I'm just gonna go over them so you guys can see it. We did this too. We did, well, how would you do this? This is a reflection. We don't refraction a lot. So that's a reflection type of problem. You see, you have two mirrors perpendicular to each other, right? Yep. Theta 1 is 39 degrees. Determine the distance the reflected light being traveled before striking mirror 2. So in what direction does the light being traveled after being reflected from mirror 2? All right. Yeah, you have to think in terms of the horizontal there. Okay, so I'm gonna draw that so I can show you that reflection problem. And then I'm gonna use this video to also show you a bit of lenses and mirrors. There is a whole lecture where I go over lenses and mirrors. So you have enough information for this, okay? This one in particular. There you are. Not bad, right? Reminds me when I used to do geometry. Student. Ángulo diedro in Spanish. Anyway, so you have this. There. And you have the normal. You have a beam of light. Like I show you in the graph, this is theta 1. This is mirror 1. And this is mirror 2. 1 and 2. The angle is of 39 degrees. There you are, looks good. Light is gonna go here and then it's gonna bounce here. And then it's gonna bounce like this. That's what light's gonna do. So 39 degrees by the law of reflection, that's also 39. So the part A is asking you, what's this distance traveled, the hypotenuse? If this is 1.25, well, 39, 39 by parallel lines. Opposite over hypotenuse is the sine of 39, right? Opposite for 39. So sine of 39 is 1.25 over, let's call it H. Let's call it X. Is X. So X goes here, this goes down. X equals to 1.25 divided by sine of 39. 1.25 over sine of 39. Again, 2 meters. 2 meters. That's the distance traveled by light from mirror 1 to mirror 2. And then respect to the horizontal, light is redirected by 39 degrees. Interesting, right? Yeah. By the law of reflection, these angles are equal. So 39 degrees. All right. Well, that's respect to the vertical. The horizontal, maybe you want to also be careful with this angle, right? This angle will be the complement. That will be 51 degrees. That's respect to the horizontal. The horizontal is no, but it's geometry and trigonometry. Refraction and reflection of light is just geometry and trigonometry. Lenses and mirrors. What do we have in lenses and mirrors? There's a whole video I posted about that. Ah, this one is good. I like this problem. I want to show you guys. So look at the number 2. They give you a dentist that uses those mirrors that they use. Those are concave mirrors, by the way. And he's going to use it to examine a tooth that is 0.75 centimeters in front of the mirror. So they put it close to the mirror so they can magnify the mirror and they can see cavities. The image of the tooth is 40 centimeters behind the mirror. Yeah. So you see, if you're going to magnify an object with a mirror, with a concave mirror, this object has to be placed within the focal length. If you have watched my lecture, you know what I'm talking about. You got mirrors and lenses, and the main parameters are the focal points and the center of curvatures, where the radius of that curvature is double the focal length. So when they tell you that the image is behind the mirror, that image is virtual. So it has a negative sign. The focal is going to be positive because it's a concave mirror. Now, you're probably wondering, well, but they don't tell me. But I'm telling you, the only way you can magnify an object with a mirror is by using a concave mirror. Convex mirrors, they always make objects smaller. That's the idea behind a convex mirror. And images of convex mirrors are always virtual. Now, here you have a virtual image, but that's because you are magnifying the object. All right? So you have the object distance and you have the image distance. Think about it. You have 0.75, that's the object distance, and 14 centimeters is the image distance. But that's negative. So then you can find the focal, you can find the radius, and you can find the magnification. So let's do it. See, lens mirrors is also a very interesting topic. I feel like that's something that many of you will like. So let's draw it so you can see what's going on. You see, you have the optical axis, and you have a concave mirror. Like this. You have the focal, I'm going to exaggerate it like this. And you have the radius here. So that's the center. The object has to be within the focal. That's 0.75 centimeters. And the image is behind the mirror. That's in front of the mirror. Look, ray tracing. If I do ray tracing here, I'll get this. And then I'll do there. That's what they're talking about. That's the image. And this is 14 centimeters behind the mirror. 1/P plus 1/Q equals to 1/F. All right. What's P? That's the object distance. What's Q? That's the image distance. And F, of course, is the focal length. Object is positive for mirrors always. But at least normally it's like that, all right? So 1/0.75. What about the image? Because the image is behind the mirror, it's negative. Negative 14. So minus 1/14. That's equal to 1 over f. And then I double the focal length and I get the values. I want to give you an algebra trick. 1 over a minus 1 over b. F is this times this over this minus this. Not this minus this minus this. Because now you do that in fractions. That's 13.25. You can use decimals if you want, guys. I'm just trying to use some of these math tricks that I know, but at the end of the day, you can use any method to simplify this. I get 0.79 for the focal. So my radius is 1.58. So then the radius is double the focal, which is 1.58 centimeters. How about that? This is a very nice problem of mirrors. What about the magnification? So these are mirror and the same as the lenses equation. For the magnification, that's negative Q divided by P. Negative 14. I already explained what's negative. P is 0.75. And guess what, guys? You are going to get a positive magnification. You get about 18.66, so 18.67. So what is the meaning of magnification? Is how much bigger the object is behind the mirror. So the image is bigger than the object by almost 19 times. Now, why is it positive? Because that means that if the magnification is positive, the image is upright. So it will be something like this. If the magnification was negative, this, it will be inverted. You probably think it doesn't matter, but it matters when you're doing experiments of optics. Okay, magnification matters because this is telling you, for example, that the image is virtual. The image is virtual when it's behind the mirror, or when it's an image that you cannot project on a screen. All right. Okay, now let's do lenses. But before we do that, let me show you something I have here. That's why it's closed right now. Well, I'm recording these videos in a spring break. We have the cabinets closed. I wanted to show you lenses and mirrors. But you've seen them in the lecture, in the video lecture. I might try to show it in another video, but that's how they look. If it's a concave or convex, it's just the other way around. What about if you have lenses? Now, in a lens, the equations are the same, but the definition of real and virtual is slightly different. For example, I want you guys to take a look at the following problem. Yeah, so you have two converging lenses with this focal length at an object that is 30 centimeters in front of the first lens. What is the final image form? So this is a classic lenses problem, right? And it's a very good problem to practice. Combination of lenses, a bit of ray tracing, and in general, it's a good problem to go over the whole idea of lenses and image formation. So you have one lens with, you know what? Let's round those numbers. I don't want to deal with this decimals. Let's make it 15 and 40. And yeah, you know, I don't know why CENGAGE likes to do that. So let's put an object and let's make the first lens. It has 15 centimeters up. 30, let's make this 30. So 15 will be around this. So let's say this is the first lens with a focal f1 equals to 15. In fact, in the lab, we don't use lenses with focal lengths like that. Normally they are like whole numbers. Both are 15. And they're placed, okay. 30, maybe around here 40. Okay. You guys can see already the graph I'm doing on the board. There. This is 40 centimeters. Both are 15. And this is, of course, 30 centimeters. Where is the final image? For a combination of lenses, guys, you have to determine, there are normally several values of object distances and image distances. You have a first lens, which is going to create an image here, and that image is going to be the object for the second lens. That's the key. And you can do ray tracing to kind of visualize what's going to happen. If I do ray tracing, by the way, the focal is 15, so it's halfway through here. So this is the focal of that. This is f1. Our lens has two focal points, by the way, because it has two surfaces. What I'm showing right now is the, interesting. Very close to the second lens. Let's see what happens. So this is P1. This is Q1. You want to find Q1. So 1 over P1 plus 1 over Q1 equals to 1 over F1, which is 50. If you do the math, guys, you get 1 over Q1 equals to 1 over 15 minus 1 over 30. If you multiply by 2, you get 2 over 30 minus 1 over 30. That's 1 over 30. This equals to this. So Q1 is 30 centimeters. Yeah, that makes sense. This is 30. So that means that that image is very close to the second lens. In fact, 40 minus 30 is 10. This is 10. That is P2. The second object distance to the second lens. So this is P2. F2 is 15. It's still a converging lens, so it's positive. So I need to find Q2. Look, guys. 15 like Like that. Ooh, they are not going to intersect over there. So what we have to do is we have to project this. It's going to be around here. If I extend this, there. My image is going to be behind or in front of the second lens, basically. It's going to be a virtual image at the end. Well, let's take a look. For the second lens, 1 over 10, that's still positive, plus 1 over Q2 equals to 1 over 15. Yeah, it's going to be negative. So what happens? 1 over Q2 is 1 over 15 minus 1 over 10. That's 1 over 2 over 30 minus 3 over 30. That's negative 1 over 30. So Q2 is negative 30 centimeters. So it's going to be quite a virtual image in front of the first lens. That's the idea behind a refractor microscope, compound microscope, by the way. So the image is located in front of the first lens, 30 centimeters in front of the second lens, sorry. That's in front of the second lens. Behind the second lens will be over there. And that's what I was saying though. For lenses, it's different. If the image of a lens is behind the lens, it's a real image because you can see it on the screen. If the image of the lens is in front of the lens, it's negative, it's virtual. So the final image is virtual, as you can see by the sign. Now, what about the magnification of the system? They ask you in this problem, find the overall magnification, basically. So for that, you need Q1, P1, P2, Q2, because the total magnification, M total, is M1 times M2. M1 is negative 30 over 30 times negative 30 over 10. And look what you get. Positive, negative, so negative 3. You get equals to negative 3. So the image is 3 times bigger than the object. Compound microscope. All right. Remember that for a flat mirror, guys, the object and the image are at the same distance. So if they tell you, for example, that you are standing in front of a mirror that is flat, your image will be the same position behind the mirror. It's a virtual image. There's no magnification for flat mirrors. All right. And for a flat mirror, the image is always virtual. All right. There's a question there that I don't want you guys to get confused. And that's basically it. I want to do office hours for this for sure, because these are interesting topics, but there is some geometry that may get some students confused. But I think this should help with assignments on lenses, mirrors, refraction, and reflection of light. All right. This problem that we just did, I just showed you, is in chapter 23. And the previous problems of refraction were in chapter 22. What's coming next is, there are video lectures on electric forces, electric energy, and current. But I will go over some of the problems on the assignment. I might throw you guys a video again now in the spring break, which is March 9. I don't know when you guys are gonna watch these videos. You may watch these videos later in the semester, but now you have it. And I feel comfortable because I think I went over a good amount of examples. I will suggest you guys to show to office hours. And this applies to any, because I'm pretty sure these videos will be watched by many students. So I always do that in my classes. I offer office hours in the weekends, or even sometimes during the school days. I teach in school. But yeah, I mean, it's up to you guys to watch the videos and then go over the problems, take a look, and then of course go over the exams. And I hope that you guys are doing the labs of this, because the labs on these topics can be very interesting. All right, guys. So I'll see you guys in the next video. Have a nice spring break, or have a nice day whenever you're watching this, and see you guys later. Bye bye.